Thank you. Cool, yeah. So I'm Hannah from the University of Leeds, and my PhD question is on what are the impact of discontinuities on rates of fluid mixing. So in this talk, it's going to be a bit abstract, and it's like models that just capture the essences of mixing in a sense. So when you standardly think of fluid mixing, you generally think of stretching and folding. So this is what you see in like turbulent kinetic eddies, or if you have like a chaotic advective velocity field. But you can also achieve good mixing through the action of cutting and shuffling. So it's the idea that you can create intermaterial interfaces and increase segregation just by cutting and shuffling alone. But where in stretching and folding, it's usually like an exponential relation in stirring. In card shuffling or in other sort of cutting and shuffling mechanisms, it's generally just sort of polynomial. You don't get this exponential-like behavior. But this continuous stirring can sort of form like an underlying mechanism in some stirring protocols. So in split and recombine micromixers, it may be configured so that the split and recombine is helped to encourage the mixing. And then granular material is also being shown to have an underlying aspect of cutting and shuffling in the bulk flow. So where you'll get the solid body rotation, you can get solid cutting and shuffling mechanisms in this part while you have like a thin flowing layer across the top. So today I'm going to present some work on looking at cutting and shuffling and also the action of molecular diffusion. So I'm just going to present basically a really simple one-dimensional model today. So what I'm using is something called an interval exchange transformation. So if you define some kind of interval of any length, but you can obviously renormalize it to the unit interval. And then we define it as a map where it's in the sense of you have a set of lengths which indicate the lengths of your intervals, and then a permutation of those intervals. And then this becomes just a pointwise map in terms of these parameters. But obviously, with a sort of this idea of that you can define any lengths, interval lengths means that I have like an infinite choice of parameters that I've got a lot to consider. So the sort of approximation that I take is that I'm going to look at a definition where I define a ratio between my adjacent subintervals, so then I can just define my interval exchange in terms of a parameter R and a permutation. And then just to show you here that you can get some decent sort of stirring happening by just this shuffle. So here I've got an initial condition along the top where I've coloured my different intervals, and then I've continued like an iteration, so like a repetitive stirring protocol of my interval exchange. And you can see that you get some significant sort of segregation after a few iterations. So there was two papers published quite recently, so Cotter et al. And Yu et al. And they were looking at finite time mixing rates and interval exchange transformations, because a lot of the mathematical foundations generally focus on asymptotic time, but an engineer wouldn't really be bothered about an asymptotic time mixing rate. So they came up with 4 criteria to say how you get good mixing in finite time. So they said that you need to choose a permutation that's irreducible and non-rotational. Obviously, a rotation will not increase any segregation at all. And irreducible just means that like a reducible permutation would sort of keep a sort of a split in your permutation. So here I've just done the simplest one. I've kept the first interval fixed, and then these ones can sort of mix around. And you can see that obviously like this stops segregation amongst the whole interval. So that one makes a lot of sense. The second one they said is that you want to choose a ratio close to 1 but not equal to 1. So this is the idea that you want your intervals to be like of a similar length, because what happens if you have a ratio that's too large, then you've got to try and increase segregation by just using very small intervals to chop up that larger interval. So that was another criteria they established. They also said that you need to have a more irrational value of R or a varied cut location. And by the term more irrational, what they mean here is that that you want it to have a longer fractal expansion. So what happens is if you choose an R, say R equals 1.5, what this means is by having a permutation of length 4, you end up after, say, like 65 iterations, and you get some rejoinings. So you get, because everything's periodic if you have a rational value of R, which obviously by computation we're restricted to. But if you make your R more irrational, so here it's R equals 1.49, you've got to sort of extend your periodicity of your interval exchange. So if you're stopping in finite time, you've got good mixing. Or if you include varied cut location, then you completely destroy the chance for rejoining to occur. And then they also hypothesized that actually they viewed in this finite time system that you get diminishing returns on the number of intervals. So they suggested by choosing just a permutation with 4 intervals would be enough. So I basically investigated including diffusion in this to see if some of these criteria stacked up, and then found some other interesting results along the way. So how I do this is that I just solve an advection diffusion equation, and I've sort of ignored the numerical way that I do this. I've just focused on the basic idea. Is what I do is I take a concentration field, I represent it by a function. I have a discontinuous stirring mechanism, so I just sort of have to apply a stirring transfer operator on my concentration field, and then I'm going to diffuse afterwards by including a diffusion operator. So here I just solve the heat equation on the unit interval with periodic boundary conditions. And you can see by including diffusion, if I have like an initial black and white condition, and you add diffusion, you get a transition to grey. So obviously this grey would be like a mean concentration field, so I can measure this transition to grey by, say, just measuring my variance or something. And what you see is that in the initial stages you have this sort of like non-exponential like behaviour where you get sort of significant decay of variance, and then you'll get this long-term exponential decay rate, which is, we can understand from the fact that we are using transfer operators. So our joint operator, which represents both the advection and the diffusion, will have a corresponding spectrum of eigenvalues and eigenfunctions. And eventually what happens is once a lot of these eigenfunctions are decaying, you're left with the slowest decaying one, which is giving back your second largest eigenvalue, because you have a trivial eigenvalue, which is equal to 1. So I was interested in the fact that, like, okay, well, I know I get this long-term exponential, but it looks like Morse mixing is occurring in this stage. So can I sort of maybe say anything about this? So one interesting result I found was, if you have chaotic advection and diffusion, generally what happens is you see that the effect of the initial condition isn't really that much, where what I found is that in these interval exchange transformations, you basically, so I just took that half black, half white as basically just a square wave representation, and just rotated it in my interval domain by a small factor, that actually when your diffusion is quite small, you can see a very significant effect on the time to achieve a mixed condition, which I'll define in a minute. By, like, say, the order of like 400 iterations in this case, just by simply rotating the initial condition. And then you can see that it's because they'll all have the same long-term decay rate, but obviously something is happening up here in sort of what this rotation and using the same permutation is doing. So yeah, so I sort of just define a time to achieve mixed condition here. So this is if you say, when does my variance get within 1% of my mean concentration field? Well, let's call that T99, and then I can plot that as a dashed line. So I'm interested in when these lines cross this. So then another thing I was interested in is going, okay, well, I have this strange thing with my initial condition, but then also what's the effect of changing the diffusion rate and the time that I can achieve a said mixed condition. What I found is that so along the bottom you've got decreasing diffusivity going that way, and then this is the iteration in which these cross the line. So you can see that for, these are the same lines that were on the colour relation to the other plot, so these are different initial conditions. But you can see that with changing diffusivity, that they all seem to give me a nice straight line on this log-log plot, so that suggested that we're getting a polynomial relation with an exponent minus beta. But beta doesn't rely on the initial condition, it's just the constant c that seems to rely on the initial condition. And I was asking questions because I'm still sort of researching why we're getting this polynomial relation that's where this beta is less than 1. Because an interval exchange transformation is mixing polynomially. So if I take my diffusion rate to 0, its eigenvalues will all tend to 1. But if you look at diffusion acting alone, which is this sort of black triangular line, you get that your beta exponent is equal to 1. If I choose like one of the irreducible permutations or one that isn't mixing very well according to the criteria, then it's also equal to 1. But I seem to get the interval exchange transformations which satisfy this criteria of Cotta and U, say in this range of diffusion, give me an exponent that's less than 1. So then I was thinking about, okay, well, where does it come from? Because obviously, like, this straight line sort of suggests that maybe those initial stages aren't that important. And then I've been looking at, actually, if you take the assumption that my mixing rate is dependent on just my eigenvalue, then you would get a proportional relation like this. So if I plot how my eigenvalue changes with diffusion, then you can see that I actually retain this relation again. So what it seems to suggest is actually what's happening in the long time limit gives a very good approximation to what we expect to see even in the finite time, even though my finite time mixing behavior isn't really exponential. So I presented a really simple one-dimensional model today on cutting and shuffling with diffusion. I found that long-time mixing rates is exponential, however, lower diffusivity gives you like non-exponential mixing rates in the initial stages. So the effect of these initial stages would mean that you actually get significant variation depending on the initial condition, which you wouldn't get for a chaotic effective system. And then the time to achieve this fixed condition is actually polynomial with diffusion, and the exponent of which is actually dependent on the interval exchange transformation. So for future work, I'm just looking into reasons of why this polynomial relation comes about, and can I define which parameters would maximize my value of beta. So thank you very much for listening.
Okay, time for a quick question. Yep.
Can you compute like of exponents on this kind of thing? If you have like locate a particle in one of your
Okay.
it gets moved around. Is that revealing at all?
No, so because in a cutting and shuffling system like this, I actually have no underlying stretching rates. So my Lyapunov exponents are generally all equal to 0. And then I've also looked at another system where I had a stretching rate composed with a discontinuous transformation, which again would mean that the Lyapunov exponents were the same everywhere, but the behavior varies depending on which cut and shuffle you tend to choose. So Lyapunov exponents don't tend to reveal anything in these kind of systems.
Okay,
Great.
thank you very much.
Hi there, so my name's Paneet. I'm a PhD student at the University of Manchester, supervised by Matthias Heil and Andrew Hazel. Okay, so the problem that I'm considering is the flow past an oscillating cylinder. So we've got an oncoming flow with speed u, and the cylinder oscillates with amplitude a and period t. What's shown below is what you find in certain regimes is you get this interesting vortex shedding pattern arising, where the green, so what I've displayed is contours of the vorticity field. Green indicates positive vorticity, red indicating negative. And what you find is after a while it settles into a time periodic state. Now, Williamson and Roshko in 1988 explored the effect of varying the period and the amplitude and how that affects the actual flow pattern that you observe in the wake of the cylinder. And what is worth pointing out is that there's quite a sharp transition between these sort of regimes. So if you notice the sharp boundaries, and that's what we want to look into. So how does this transition take place? So is it a case that we've just got one solution to Navier-Stokes equations and that evolves as you change these parameters? Or is it a case that we've got, say, two different solutions? One might be unstable while the other is stable. And then as we pass these boundaries, there's one, they switch stability. That's why we observe one and not the other. So to actually analyze the time periodic solutions, we need a method of actually being able to calculate them. So that's what I'm going to talk about now. So the simplest possible case, you just formulate the problem as an initial value problem and integrate the equations forward in time. Now this is a conceptual sort of diagram of what you might observe. You start from some arbitrary initial state, integrate forward sequentially, and over time you hope that you arrive at the time periodic solution. Now, in the case that if the transients take a very long time to decay, then this method becomes extremely expensive. Worse still, if the time periodic solution is unstable, you'll never actually arrive at the time periodic solution. So another option that we've adopted is a spacetime formulation, which you can think of as having x and y as normal, and then time takes the place of z. And what we do is on the time boundaries, we enforce periodicity, and what that gives us is the time periodic solution directly. And then that means that we don't have to compute for all these transients, we just jump straight for the time periodic solution. Great. What we also find is that we are also able to compute unstable time periodic solutions as well, which is quite handy. But the downside is that you've got a huge 3D system to solve, which is going to be expensive. Which means that we need an efficient solver. And I spent a lot of time doing this, but unfortunately, in the interest of time, I can't mention anything about it, but feel free to ask me after the talk. All of this machinery that we've implemented has been done in UmpLib, shameless plug. And in the case of time integration, this is the sort of simulation mesh that we've got. What we find is that what we do is we just distort the mesh as the cylinder oscillates, and we've got this red node here, which I monitor the solution at, and it's quite a good indicator that if the time periodic solution at that point has become periodic, then it's a good indicator that the full velocity field has become time periodic. Now, why might that be useful? So if I'm running loads of different simulations, it might be hard to analyze the full velocity field all at once, whereas if I've just got line data, I can iterate through them quite easily. Now, in the case that I've got a space-time problem, I've got my x and y as normal, and then time goes in that direction now. And you can see that the cylinder traces out a path here in the time direction. Okay, so that tells us how we're going to compute it. Now, what I'm going to tell you about is how, what I'm actually going to look at. So I'm going to look at the transition between the 2s and the p plus s regime. So on the left, I've got a phase diagram that was developed by Leontini by running a lot of time integration simulations, and he varied the period of the cylinder oscillation and the amplitude, and looked at what the vorticity pattern that he recovered was. So the 2s is associated with the shedding of 2 regions of vorticity per cylinder oscillation, as you can see in this unit cell here. Whereas the p plus s is associated with the shedding of a pair of vortices and a single separate vortex per cylinder oscillation. What I want to analyze today is how I transition from one solution to the other. So these are the 2 pictures that you just saw on the previous slide. So this is at a low amplitude and this is at higher amplitude. And what I want to see is what happens in between. Unfortunately, this is a prime example where the transients take a long time to decay. So we can't use time integration because it just becomes too expensive. So instead, we try the space-time formulation. And at low amplitude, the solution agrees with what we found in the time integration. And then as we increase the amplitude, the solution also agrees with the time integration simulation. But now, what we can actually do is just decrease the amplitude slowly and then compute the intermediate time periodic state. Okay, what I haven't actually told you is this is all inside a big Newton solver, which means that it needs a good initial guess for the solution. Now, what I've actually done is I've taken this time-integrated solution here, and I've copied it onto the space-time mesh. And I slowly decrease the amplitude to get the solution here and the solution here. Okay, so this is the first method. Start at high amplitude and decrease slowly. Second method was to start at low amplitude, and then what you see is that all simulations agree, and then I increase the amplitude slightly, and look, they're slightly different. And as I get to the sort of peak amplitude value, what we find is that the solutions are completely different. So on the first one, we had a p plus s solution, whereas on the second one, we've still got the 2s solution, hinting that this might be an unstable solution that no one's been able to see with regular time integration. So we've got multiple solutions at the same amplitude. Now, what I want to investigate is where this deviation comes in. Where's the sort of precise point that this happens? So on the left, what I've displayed is a time trace of the horizontal velocity at the control point over an entire period of the solution. So this might be obtained from either starting at a high amplitude and decreasing slowly, or starting at a low amplitude and increasing upwards. And what we find is at low amplitude, they agree, which we saw on the previous slide. And if I set this off running, the velocity field evolves as the amplitude increases, but the solutions still agree. And then as I get to about here, if I slowly increase the amplitude, they start to deviate. And then you can see that there's an interesting character where the solutions definitely deviate away from each other. Okay, so what does that tell us? So what we find is that the change in the vortex pattern between the 2s and the p plus s wait mode arises from a bifurcation of the Navier-Stokes equations at this critical amplitude value. Unfortunately, this is hot off the press, so we've only just discovered this in the last week or two, but we thought it was very interesting, and this is what we're up to so far. So in summary, I've developed an efficient solver to compute time periodic solutions directly, and I applied it to investigate the transition from the 2s to the p plus s wait mode. So what's quite nice about this solver is the fact that there's this classic case where the transients took a long time to decay, and time integration just wasn't feasible, and there was this presence of what we expect to be an unstable 2s solution at large amplitudes that people haven't been able to compute because they use regular time integration. So this is where it comes into its own. And obviously the main result that we've discovered so far is that the change in the vortex pattern from 2s to p plus s arises from bifurcation in the Navier-Stokes equations at this critical amplitude value. Thank you.
Okay, so time for some questions. Yeah.
So you found these two solutions at the same value A.
Yep.
Are they both stable, both unstable?
So that's something that we need to investigate properly, but we kind of argue that one's stable while one isn't unstable because when you use time integration, it naturally tends to go to the P plus S solution at high amplitudes, but no one's really been able to observe this 2S solution at high amplitudes. But what we need to do is sort of take a closer look. We need to get closer to this actual bifurcation point here. But the Newton solver, when we run it, starts to diverge there, so we need to implement some arc length continuation to carry on that curve and exactly find out what happens local to that bifurcation.
Okay. Yes?
Have you validated this result with the experiment? I'm not sure that this is physical.
Well, you wouldn't observe it physically because it's unstable, but it'd be very hard as well to get it in an experimental study because as soon as you apply a small perturbation to the system, it just deviate away from it. So I'm not sure how to validate it experimentally, but the P plus S one and several other vortex patterns you observe, it's ubiquitous in nature.
So,
Jacob.
how do you deal with the physics terms in terms of the stability, like Laplacian terms? Let's say pressure of x squared when it comes to stability issues.
Sorry?
How do you deal with stability issues when it comes to the physics terms in your solution?
The instability and
Stability.
stability of the solution.
Yeah, of your solution when it comes to Laplacian terms.
I'm not sure I understand, sorry. We can have a talk about it afterwards if that's easier. Are there any?
Time for a very quick question if anyone else had one. Yeah, go.
Just to recommend that the parameter A, is it linked to the amplitude of displacement or the acceleration?
So it's the amplitude of the displacement, but it's non-dimensionalized on the cylinder diameter. Yeah. Oops. This is a bit noisy.
Okay, thank you very much.
Thank you for the introduction. Good afternoon, everybody. So my name is Alessandro Marino. I am a PhD student at the University of Strathclyde in Glasgow. And today I'm going to introduce you to this big part of my PhD project, which is the investigation of exactly of the application of these biomimetic tubercles on the drag of a flat plate. So briefly what I'm going to tell you is I'm going to give you a brief background on what the tubercles are, on the research that has been done with them so far, on what I have been doing with this. And so I'm going to explain to you what my geometrical model looks like and the results I've got so far with the numerical simulations. So you may be or maybe not familiar with humpback whales. These very huge cetaceans are particular because they got very bulky bodies, and despite that, they're able to perform very sharp and fast movements. So researchers started to concentrate on their physical feature as the tubercles you may see here, for example, on the leading edge of their pectoral fins. And I'd like also to draw your attention on the tubercles in forms of bumps that you can see on their nose, but I'll go back to that later. So here it's very, very clear. You can see that the leading edge of the pectoral fins of these whales have got these tubercles. They have been studied in many applications, for example, by Dr. Shi during his period at Newcastle University. He applied sinusoidal tubercles mimicking the actual ones to the blade of a tidal turbine. And he found out that the presence of these tubercles generate counter-rotating vortices which attach the flow to the surface of the foil of the blade. And so they delay the detachment of the boundary layer and hence the stall. So they enhance the performance, basically. This is pretty clear from these graphs. You can, maybe it's not very clear, but because it's only black and white. Anyway, the lift coefficient shows clearly that the lift of the blades with the tubercles is higher than the one of the smooth leading edge ones, especially at high angles of attack, and it doesn't show the sudden drop typical of the stall phenomenon. This is very interesting, of course, and on the other hand, the drag coefficient is very slightly increased. So the overall performance, which is very well described by the lift-to-drag ratio, is increased all the time by the presence of the tubercles. Some other results from the US, for example, Gruber and other researchers studied similar patterns on tidal turbine blades, and they found out that the tubercles decrease the cut-in velocity of tidal turbines and give a higher power coefficient. So, but now what I am working on is this other kind of tubercles, the bumps that you can find on the nose of the whale. So, do they have the same effect? Do they create these counter-rotating vortices? This is basically what I'm after. So, what I'm going to present now is what I've done so far with the application of single rows of axisymmetric sinusoidal tubercles at different positions along the streamwise direction of a smooth flat plate. Maybe it's easier to show a picture. So I modeled a flat plate, and I put some sinusoidal tubercles on it. So I've got three different, as you can see, yeah, the profile is the same in each direction, always a sinusoidal curve. So in all cases, I've got 10 tubercles, span-wise, with a height and length and width of 5 millimeters. I've got three different cases. A row at the upstream edge, one at mid-length, and one at the downstream edge. And these are the characteristics of the plate, of the bare plate. So I simulated a range of speeds between 2 and 10 meters per second. So Reynolds number range from 3.4 times 10 to the 6th to 1.7 times 10 to the 7th. So a little bit of results in order to show you what I've seen so far. This is the pressure distribution along the flat plate, the reference one, pretty straightforward. When the tubercles are applied, there is a remarkable change in the pressure. Okay, I put an obstacle in the boundary layer. This is what I would expect, but actually it's there. This is a really good achievement, I think, because actually it was very difficult to find something like this because there are very, very few studies on this type of tubercles. Same happens when the tubercle is at mid-length and downstream. I'm sorry, the red curve shows the pressure at the trough between the tubercles, the blue one at the tubercle peak. According to the pressure distribution, there is a change in the flow velocity, of course. These pictures show the flow velocity streamwise on the x direction. The darker color shows a higher speed of the flow. So as you can see, of course, the flow accelerates in the trough as well as on the peak of the tubercle. This happens in all cases. Mid-length, peak again, and then downstream, trough, and downstream at the peak. This led to something interesting, and these pictures show it pretty well. Basically, this is an isosurface showing the upper limit of the boundary layer. This part can be ignored, as this is the way star CCMs shows that the flow before the plate is uniform. So let's start looking at it from here. The flow is very attached to the plate at the position of the tubercles, and then there is this bump with a lower velocity gradient. So same happens when the tubercles are downstream with two big bumps before and after the tubercles. This is very interesting. And same here, a small bump before the downstream tubercles and a big bump here. This is a cut of 2 tubercles only. Of course, the plate actually had 10 tubercles in that row. I've said these results are interesting because when we compare the drag produced by the plate with the tubercles, we find this. So all cases showed a higher drag with respect to the one produced by a flat plate. All cases but the one with the tubercles at mid-length, which is the green curve here. At all speeds, it showed an increase in the performance, so a lower drag, with a gain up to 9%, which was something extremely interesting to see, and this is where I am going with my PhD now. In fact, the next steps will be now to go on with the numerical simulations to find an optimum in terms of tubercle shape, number, and spatial distribution, and then proceed with experimental work, especially with the fully turbulent flow channel that we're going to build at Strathclyde, and I'd like to spend a few words on this at the end of the presentation, and with towing tank tests. So with tubercles on flat plate, curved plates, a ship's model, and so on. So I said that I'd just like to say something, because this facility will be the main part of my experiments. It will be high aspect ratio testing section where we can drive the flow, a fully turbulent flow, up to 13.5 meters per second, and measure the pressure drop along two plates that we can put at the end of the testing section. And these plates will be, of course, flat and horizontal, but they can be smooth, rough, painted with marine coatings, and they can feature items such as tubercles or riblets, which is something other researchers have been dealing with, and so on. And so this is what I'm going to do, hopefully at the beginning of next year when the facility is ready. These are some reference to the papers I've mentioned during my presentation, and that's me with it. Thank you very much for your attention. Please ask any questions if you have.
Any questions?
34.
I consider your part as your project.
Sorry. The graphs actually show.
Without this part.
Yes, because these graphs actually show, here you can see it in here as well, they show the difference between the reference pressure and the one that is measured. The reference pressure is the initial pressure of the flow, the one I set at the beginning of the simulation. So that's why it shows a 0 in there. So there is a drop in pressure at the upstream edge of the plate, another one at the downstream edge, and then sorry. When I cut the plate, the two planes are symmetry planes, and then the far end is a no-slip wall.
Okay, another quick question.
What is the length
Can we have the next speaker?
the length of your boundary layer?
The length of the boundary layer, it goes up to a few millimeters in this at the top speed. I can't recall the actual number, but I got it with me over there. We can have a chat about that if you want. Yep.
Thank you.
Thank you very much.
So thanks for the introduction. Like he said, I'm Paul Bartholomew, and this work has been funded by Embedded CSE grant from the Archer National Supercomputing Facility. So to briefly give an overview of my talk, I'm going to explain why we want to implement this low Mach number solver within InCompat3D. For those of you who don't know what the low Mach number approximation is, I'll quickly go through that. I'll then introduce our new code, which we've named QuasInCompat3D, and then finish up with some results and conclusions. So there's been a few talks already regarding InCompat3D. It's a high-order Navier-Stokes solver for incompressible flows. Some work has been done previously in simulating sedimentation processes of like
silt, for example, emptying into a basin at the exit of a river. However, due to Incompat3D being an incompressible solver, you're limited to the Boussinesq case, where your density difference is less than sort of order of 1%. So we'd like to be able to simulate flows with more significant density variations, which is the motivation behind this work. So when these density variations are significant, we can't assume the flow is incompressible anymore. Or in other words, it becomes a compressible flow. But at the same time, our flow velocity isn't necessarily high. Specifically, the Mach number can still be very low. So if you were to just apply a compressible flow solver to this directly, it would be very computationally inefficient because you'd have to resolve timescales determined by acoustic processes, whereas the phenomena that we're looking at might be on much slower timescales. So what the low Mach number approximation does is we've termed this product here as epsilon, and we take our flow variables and we expand them in a power series. And then when you plug these power series back into the governing equations, you can take the lowest order terms. Basically end up with a system of equations which look largely the same as you started off with, but the main thing is the thermodynamic pressure becomes constant in space. So essentially we get rid of all of our acoustics, and we're left with just the mechanical pressure driving the momentum equations. For the rest of the talk, I'm going to drop all these superscripts apart from on the pressure for clarity. So the basic algorithm follows largely what you do for an incompressible flow, except for we have this additional first step where we advance either density or temperature in time. Having the new temperature field allows us to compute what our velocity divergence constraint is going to be. And then we use a fractional step method to advance our momentum equations. So basically we compute this intermediate momentum field, which we then correct using the new pressure field, whose computation I'll get to in a minute. So to do this, you could either directly take the divergence of your momentum equations, which would be the most straightforward approach. And this gives you the constant coefficient Poisson equation, which is nice because as a constant coefficient equation, we already have a fast solver for this. So we can get machine precision solutions directly. However, we don't actually know what the divergence of our momentum is going to be in the future. So to get around this problem, we can approximate it by taking a backwards difference of the continuity equation. Unfortunately, this introduces an error term, and this limits this approach to density ratios of order 3 to 5. Some people report 7 in the literature. As an alternative approach, if you divide your momentum equation through by density before taking the divergence, you end up with a variable coefficient Poisson equation, which is actually these final terms of what's shown over here. I've written it in this altered form where we recover essentially an iterative approach where we can still use our fast Poisson solver to solve this entire equation, and you iterate until eventually you reach a converged solution. Unfortunately, this iteration might potentially be very slow, but we do know what our divergence is going to be, so there's no approximation required for this equation. And also, this rho tilde term is essentially a scaling term, and it's a free choice, so we can mess with it to try and improve our convergence properties or the stability of the iteration. So one of the main objectives of this work was to enable variable density flows using Incompat3D, but maintain its performance. So we've benchmarked the code on Marconi and the Archer supercomputers, And these tests are between 2 million to about 100,000 cells per core. As you can see, we maintain good, strong scaling up to approximately 16,000 cores on the Archer supercomputer. So the first test case I'd like to present is the non-isothermal mixing layer of Golansky et al. You have a hot and a cold stream, as illustrated by this diagram. And using the constant coefficient, the variable coefficient Poisson solver, both using for Rotilde either the minimum density, which is what's widely used, and because it promotes stability, or we've also found that using a harmonic interpolation of your density field gives you most of the stability properties, but also allows faster convergence, as I'll show in a moment. We have good agreement in the results across the board and also with the reference data, and similarly for density profiles. And so here I'd like to show the relative performance of the different solvers. So our constant coefficient solver is approximately 10 times faster than the variable coefficient. And that's because basically you're spending your entire time solving the Poisson equation iteratively. However, by changing how we've calculated Rotilde, we get approximately 2 times speed up relative to the standard approach. And what you gain by spending all this time solving your Poisson equation is if you compute the error in the divergence of velocity, we're almost at machine precision, whereas it's significantly higher for the constant coefficient Poisson equation. So to finish up, the last set of results I'd like to show is we're working on some gravity currents. These are two-dimensional benchmark cases of Biermann et al. And what you can see is going from Boussinesque to decidedly non-Boussinesque, you get this increasingly asymmetric flow pattern, which qualitatively agrees with their results. And then more quantitatively, we've computed the energy budgets. And so Biermann only gives data for these two density ratios. And as you can see, you get very good agreement with their data, which is the white points, and ours are the black points. And also, as the density ratios increase, you observe that the potential energy is more quickly converted into kinetic energy, as you would expect. And so currently, what I'm working on is some 3D simulations of these gravity currents to extend the work done previously beyond the Boussinesque limit, because no one's really simulated these for long time evolutions. So to conclude, we've implemented a Lomac number solver in IncoPact 3D. We've maintained its performance. And to finish off, I need to basically complete the validation for the lock exchange and continue investigating the 3D cases. Thank you for listening, and any questions?
No? I had a question.
Okay.
Yeah. So how would you plausibly expect the density currents to change? Because obviously they're highly turbulent flows, and in 2D approximations of turbulence is not a very good one. So plausibly, do you think like the high is similar or?
So in sorry.
Well,
Oh well. Sorry. Yeah. In 3 dimensions, you after about 10 non-dimensional times, you observe a change in how the energy is being dissipated. At least in the Boussinesque case.
Fine, right?
So, I need to actually check the non-Boussinesque case.
okay, thank you very much.
So hi, my name is Gaurav Madhav. I'm from the University of Leeds, and I'm going to give you a crash course on data simulation and how we are currently using it to predict chaotic behavior in rotating fluids. So I think we can all hopefully agree that all models we use are imperfect. We all have assumptions in our models. We all have idealizations in our models. And these imperfections over time can lead to big differences in what we actually observe in our models to what we actually observe in reality. So there needs to be a way to actually get our models to a better state of behaving like what we see in reality. So what normally people do is just increase the number of resolution that they have in their model and run it on a supercomputer in the hope that it gives us good results. But running on a supercomputer is highly intensive when it comes to processing power and the time it takes. So we propose using data simulation to do this. Because with data simulation, you can keep the accuracy of the high resolution runs that you do, but you can decrease the computational time and the cost. And you can also reduce, doing this, the discrepancy that you have between your model and the reality. So what is data simulation? So let's quickly talk about how the weather is predicted. The Met Office has their weather models running on the supercomputer on their site. And then every 6 hours, they take observations from their satellites and their weather stations around the globe. They put it all together. They compare their observed data to their model data. They then find some statistics between this observed data and model data. And then they correct their model using the statistics. So this idea of actually taking your observation and correcting your model is what data simulation is. And after you've corrected your model, you can restart your model from that initial point. And then the idea being the more frequently you do this correction, the closer you are to reality. So we're going to be using something called the ensemble Kalman filter. So the X here is actually your model, and M is the number of repetitions you do to create your ensemble from this model. Y here is your observation, and the big R is your observational error. So So the first thing you do is actually you use your ensemble to find something called the covariance between all your ensemble members. After that, using your observation error, you find something called the Kalman gain, which is here K. And using that Kalman gain, you can solve your equation, number 5 here, to get your new initial conditions for your model. And then you can put that back in, and hopefully everything works out fine. So what we want to do is actually apply this to a thoroughly rotating annulus. Here you have 2 cylinders, both rotating in the same direction, in the same velocity. And the inner cylinder is cooled, and the outer cylinder is heated. So if you want to think of this in terms of atmospherics, you can think of the cooler inner cylinder being the North Pole, and the outer wall being sort of the tropics region. So depending on how fast you rotate the cylinder, you can get different patterns forming, like you see over here. So the code we're using to simulate this is called the Morrell's code. It's maintained at the Atmospherics and Planetary Physics Department in Oxford by Peter Reed. And it solves all the fancy equations that we want to, like the Navier-Stokes equation, heat equation, mass continuity equation. It uses finite difference. It was written in 1970s, so it's quite old. It's in Fortran 77. And it's sort of been, parts of it has been updated to Fortran 90. So the one initially good thing about this model is that it uses a stretch grid. So there's more grid points at the walls, so we can better resolve the boundary layers, which is pretty good for us. And the other thing being it's a staggered grid, so all your variables, U, V, W, and temperature are stored at different points, so you don't get errors in terms of averaging and calculations. So let's come to our twin experiment setup. So obviously, we're solving everything in cylindrical coordinates. All the results I'm going to show you, the rotation speeds were 1 radians per second. We're measuring all 4 variables, V, W, U, V, W, and temperature. So we first did a high resolution run, which was a 96 by 96 in R and Z and 64 in the phi to create what we call our truth run. And that took us about a week. And this has some 2 million vectors in it that needed to be recorded and stored. For our model itself, we're doing an ensemble of 10. And the resolution for this low resolution model is only 24 by 24 by 64. So we've kept the 64 in the phi because it helps with the diffusion of our energy and other variables as the system rotates. So in all our results I'm going to show you, we only observe around 2,300 points. So we chose this really extreme case just to test the ensemble Kalman filter and to see how much we need to push and tune the filter to see if you can actually track our observations. So here, the first contour plot, I don't know if the, is it this one? All right. I was just holding the wrong way around. So the first contour plot here is a slice through our cylinder in the middle, and it shows the average of the U velocity for all the ensembles. So this is the ensemble before we do any data assimilation on it. So we've run the ensemble, we've run the system for 300 seconds, and we're going to do our first data assimilation at this point. The middle contour plot here is our actual observation, so it's the truth, and you can see it's nicely an M3 mode. And the right contour plot here is what the system actually corrects the model to, the average to. So the graph at the bottom here is showing the U velocity in the middle of this. So if we go around the R here in the middle of all the phi. So the black line here is what the U velocity is in our truth. So you can see it goes nicely from positive to negative, giving us all the amplitudes and everything. The blue line here is the average of our ensemble, so down here. And all the thin lines here are different ensembles. Okay? So this is our first data assimilation step. And we are doing data assimilation at every 5 minutes. So every 300 seconds, we stop our model, we do the data assimilation, and then we restart our model with with the corrected initial conditions. The other thing we're doing is we're adding a small perturbation to our initial condition. So in this test, we used a standard deviation of 0.05 to create a Gaussian, and use that to perturb our initial conditions to run them again. So by the end of our data assimilation, which was around 5,700 seconds, we see that what has happened is all our ensembles has actually converged on top of each other, and our ensembles have diverged to the actual observation. So what has happened over time is that the data assimilation has corrected our ensembles to be closer and closer and closer to each other, and not the observation itself. And now it's really hard for the data assimilation to actually kick the ensemble in the right direction, because they're all stuck in some other mode, and they're locked in that mode. So what we actually need to do is actually inflate the ensembles so they cover more of the state space, so the data assimilation can have a better time to actually pull these individual ensembles towards the correct path, so we can better track our observations. So to do this, we ran a simulation without any data assimilation, and we looked at the standard deviation of our so to do this inflation, what we actually do is there's two types of inflations. You can either multiply your covariance that we work out, or you can actually just increase the perturbation at the end for your initialization. So we're going to do the second bit. Ideally, you want a combination of both, but we're just going to look at the second bit, because that's much easier to do. So what we did was we ran a simulation where we did no data assimilation, and we looked at the standard deviation of our 4 different variables, U, V, W, and temperature. And using that, we came up with a standard deviation that we should use for each of these. And again, we start off with a fairly robust spread out ensemble, which is good. And we do some correction at the first data assimilation step, and we get some sort of results, which is nice. And then we just let the system do its thing. And at the end, we see actually it's done a better job of actually tracking our observation, which gave us hope that we were on the right track. So the obvious thing to do now was to, okay, let's just bump up the perturbation to see what happens. So we bump it up to twice that perturbation, and now we see, oh, actually, we're spot on now. So I've added an extra contour plot here just to show you. So this contour plot is actually our correction, and this contour plot is what the data looks like once you add your perturbation. So it's quite noisy. So the 5 minutes actually gives it enough time to actually calm down and go back to a steady state like this. So now that we are happy with that we're on the right track, we can do some more fun things. So here what we were doing is we were observing only 9 points in the middle of each phi, right? So now we can play around with our actual observation points as well. So here we're using random 9 points in each phi and doing the same thing, and we actually find that, okay, we're actually doing quite well. Let's try something else. Let's try 2,304 random points in the model and see if the system does well, and it's doing quite well now as well. So the one thing I want to add before I finish is this high-resolution simulation that we did for our truth took about a week. This data simulation that we did only took 12 hours. So instead of wasting a whole week, we have done everything in 12 hours and been pretty good at tracking our observations. So we have quite good hopes that we'll be able to do more things when it comes to more chaotic behavior, which we currently have some results for. And we have actually experimental results as well that we're going to start plugging in. So yeah, thank you, and any questions?
Quick question. Yep.
So when you do inflation, you can use a hyperparameter measuring how much you inflate. How do you know if you don't inflate too much?
Yeah, I mean, we just tried tuning it to different parameters to see which one works the best, and that was the only way to actually find out how, because there's no standardized way to actually do it.
Okay, I think we'll hold it there. Thank you very much.
My research is focusing on the closed-loop flow control over truck trailers to reduce drag and improve fuel efficiency. So currently with square-back truck trailers, the flow over the back of it, there's a large separation and it causes a large amount of drag because of the size of the wake. By controlling the flow over that and reducing the size of that wake, we hope to reduce the drag on the body and therefore improve the fuel efficiency. The way a closed-loop control feedback scheme works is that you have sensors located on the truck body that measure the state of the outer flow. They send a signal to the controller, which in this case will be extremum seeking, and then that controller sends a signal to the actuator to tell it how to modify itself so it changes the outer flow, and then the sensor reads that new outer flow state and it goes around in a loop. So why is it important? Companies spend a lot of money transporting goods around the country. And by reducing the fuel consumption by just 12% across the country, we can save £1 billion in the UK alone. So obviously when you upgrade that when you take that worldwide, you can save a lot more money. The whole system will have environmental benefits as well. You'd have reduced fuel burn, so there'd be more fuel available for other areas. You've got less CO2 emissions because you're burning less fuel. And the whole system could eventually maybe be adapted for other industries to help reduce fuel consumption there. So I'm using for this a 3D armoured body with a 25-degree slant at the back. It's not exactly the same as a truck trailer, but the good thing about this model is there's a lot of data available for it for validation. And as for validation, I'm using experimental results from the knowledge base. So why aren't jet actuators used already? They require a massive power input, and so in a lot of current setups, they don't actually improve fuel efficiency because they use more energy than they save. A lot of the current setups, test setups, use an open loop system where basically they set a value and then they leave it at that value. So you have to set that value a lot higher than it necessarily needs to be to make sure that you are getting the best drag reduction at the highest speeds. So there's a lot of wasted energy in there. By using a closed loop system, it can adapt to the environment and should get less wasted energy. So the jet actuators I'm planning to use are synthetic jet actuators. They use a vibrating diaphragm in a cavity, which causes an oscillatory blowing and suction motion. The reason I'm using this is because it saves weight because you don't zero net mass flux. So you don't have to store fluid to eject from it like you would with a steady jet actuator. And a lot of the literature that I've read claims that you can get similar amounts of drag reduction with synthetic jet actuators with a lower power input than with steady jet actuators. So extreme seeking control is a slope seeking algorithm. So you pick a variable and it will minimize that. So in my case, that'll be the drag on the truck. We're trying to minimize that. So the algorithm will find the gradient and it will go down the gradient to the minimum value. The good thing about this is that it doesn't require any model information. So it's just plug and play on whatever model you're using. And it will, in most cases, it will converge to a local minimum. The downsides of this is because it's a local minimum, it may not be the global minimum. But so you may not get the best results, but you'll get some good results. It can also take quite a long time to converge, meaning that it's not great for real-time closed-loop control. But as a baseline case, it will work quite well with constant inlet conditions. So I plan to put a synthetic jet actuator on the back of my armoured body and then have the extreme seeking control modify the frequency of the vibrating diaphragm. And when in the CFD simulations, I can measure the drag coefficient directly. But when it comes to the actual experiments, I'll have to find a new variable to measure to indicate drag. So, like I said, in CFD you can measure the drag coefficient directly. But when it comes to experiments, a lot of the literature suggests using pressure coefficients because they can be indicative of drag on the body. So what have I done so far? I've investigated various turbulence models for my simulation. I've looked at various 2D simulations using those models to work out what would be best for my flow. And then I upgraded it to a 3D armoured body simulation. And I settled on the realizable K epsilon model with non-equilibrium wall functions. And I would like to have shown you some results from the simulation today, but I had some issues with the CFD validation in that my drag coefficient was twice the size it should be, which means that it threw out a lot of the results because it's all based on drag coefficient measurements. But taking into account what the literature reports on synthetic jet actuation performance and the extreme seeking control performance, I hope that I have a good, I'm fairly confident that it will provide a good baseline for future experiments. And with that, the actual aim of my PhD is to develop a model-based control scheme. So I plan to use the information from the CFD simulations that I'm running to get a better control scheme than the extreme seeking, which should allow it to converge much quicker than the extreme seeking, and therefore improve efficiency and reduce the wasted energy in the whole system. Thank you. Any questions?
Time for a few questions. Who wants to start us off? Yes, go on.
So do you envisage, when this is used in anger on a real truck, that the CFD would be run by the system, and you should do have a whole load of CFD done offline and have some sort of lookup table that the system can then refer to in operation?
The plan would be to do the CFD before it's put on the body and then have some sort of lookup table, or because it'll be used on standard truck body. Like a lot of truck bodies are standard square back bodies, so you wouldn't need to necessarily run lots and lots of different simulations because the flow around the body will be very similar.
And so how would you take into account of other things that might be present when your truck is driving on the road, like going under a bridge, passing another truck, stuff that?
So that is something that we were planning to look at after the initial thing. And because we're using a closed-loop system, it should be able to adapt to external factors. So things like wind speed changes and wind direction changes and things. So eventually the closed-loop system should be able to take that into account.
So I had a quick question about the case that you're looking at. So the Ahmed body with the 25-degree slant, it's quite a different type of separation to your abrupt rear end.
Yep.
Have you looked at, provisionally, with the synthetic jets, are going to be strong enough to have an influence on that more severe separation?
Not at this point, but the plan is, so at the minute it's a 25-degree Ahmed body, but that's because there's a lot of data out there to validate against. Once I've validated the model and I'm sure that I'm happy with it, then I was going to move to a square-back Ahmed body, so I could test whether they're strong enough there.
Makes sense.
Yeah.
Yeah, go on then.
Is there a scope in the project to study different arrangements of actuators over the surface, and perhaps on the front of the trailer and along the roof line or along the side?
So there is, I discussed with my supervisor like optimal locations for it, and there is that is a whole other topic of there's lots of different places you can put them. We're focusing primarily on actuators at the back of the truck and the separation at the back of the truck, but there is a lot of scope for actuators being placed in other locations on the truck as well.
Adrian, if you want to start setting up, there's probably time for a final question if someone wants to take it. Yes, go on.
Do you consider the above the actuation of the
Sorry?
Do you think that above the actuation of the when you calculate the energy of losses, or you just focus on the drag function?
No, so a lot of the studies at the minute don't take into account the energy required. I plan to take into account the energy required and match it with the drag, so it's a net energy saving rather than just a drag saving. Sorry.
Okay, thank you very much.
Okay, thank you very much. So, first of all, I'll start off by kind of cutting through the jargon of the title. So the idea of a heterogeneous mobile cluster, essentially it means devices that are portable, but all have different hardware. So it could be different processors, different amounts of memory. And essentially what I'm referring to here is, of course, things like mobile phones and tablets that you carry around with you. And this is actually a project that's part of a bigger research theme, if you will, which is to try and explore exactly how we organize and implement numerical simulation algorithms such that they're suitable for the different design of mobile hardware versus desktop systems and workstations and HPC clusters that perhaps we're already accustomed to implementing algorithms on. So, you'll probably notice that mobile phones are practically everywhere. Okay? They're an extremely prevalent and affordable computing resource. And arguably, the things we actually do with mobile phones really don't exploit the computational potential of these devices. So, of course, the broader research theme that I'm looking at is actually, can we leverage the potential, the computing potential of these devices collectively to actually do something useful for engineers and perhaps to provide services in other applications. So in fact, thank you for the previous speaker. It actually gave me an idea as to perhaps one application for running very, very fast simulation, which is actually what I deal in real-time simulation. You could use it to dynamically control systems by taking information in from the outside and then using that information to perform some very fast modeling and simulation that you can then adapt particular actuators to modify a situation. So that's essentially what I'm looking at. It's real-time CFD and super-fast CFD. And this was a proposal that we put forward in a paper last year as to the way we would achieve that is actually to use mobile devices as a kind of interactive tool. So they provide touch screens and all sorts of interesting features like that. We can actually steer our calculations by essentially drawing on the screen to represent geometry, using the cameras to try and capture a physical environment. But then can we actually do the simulation we want on the device itself? Or in fact, perhaps we could offload it to a cluster of devices, or indeed an HPC cloud facility, or a whole range of other computing resources that form our real-time compute engine. So this was the real idea, and what this talk does is actually build on a couple of previous papers to actually explore how we can use mobile devices to do this interactive simulation where, as I'll reiterate, we can actually steer our simulation as it's running without having to do remeshing. We can actually just modify some of our simulation parameters, change the flow speed, and inspect, of course, what's happening with the flow in situ without having to visualize things offline. And this is what an earlier paper proposed. It was 2 different strategies to do this on a mobile CPU. Now, the method we use for our CFD simulations is the lattice-Boltzmann method. There's probably been a few talks that have mentioned this at some point. But essentially, it's a very, very efficient method to parallelize on things like GPUs, things where you've got many, many threads working at the same time. You can also parallelize it on CPU, and we actually measure performance of lattice-Boltzmann in what we call million lattice updates per second, which I've shortened here to MLUPs. And just to put it into perspective, if you do CFD using parallel strategies on mobile CPUs, you get about 1 MLUP. Okay, it's pretty poor compared with what you would get running it on a big supercomputing cluster, but that's of course because mobile CPUs are geared towards energy efficient calculation. But it does scale quite well with, in terms of the number of threads you can run, but of course there's a maximum limit to how many threads a mobile CPU will also support. So we're dealing with some hardware constraints here, but you get about 1 MLUP. So we moved on in a follow-up piece of work where we actually said, well, let's use the GPU on mobile phones. Since mobile phones now often come with a dedicated GPU, okay, it's scaled down from a desktop card you might have, but it still has quite a lot of potential. So this was a particular architecture that I used to implement an interactive CFD app on a tablet that had a Tegra chip on board the tablet. Now, because it's a Tegra chip, it's an NVIDIA piece of hardware, therefore we can use CUDA. So I implemented lattice-Boltzmann using CUDA and had that run on a mobile device that had a Tegra chip inside. This is essentially how it's scaled with resolution up until a threshold where essentially you saturate the memory bandwidth of the GPU on the device. But we found that you could at least get a nice 13.4 throughput improvement by using the GPU on the device. And crucially, when we monitored the battery consumption and the power consumption of these tests, we actually found it was 22.5 times more efficient as well in terms of battery drain by using the GPU. So you combine it together, you get quite a big improvement in terms of power efficiency. Again, the references are kind of along the side here if you wanted to look them up. So then we moved on to what I'm talking about today, which is, can we combine multiple devices together to essentially spread that calculation over a room full of mobile phones? Now, I was very tempted to bring on a couple of tablets along and stick one in each corner of the room and then just have the calculation run across these points across the room. But I didn't want to err on the side of the talk turning into a kind of Apple product launch, so I thought I'd leave that one at home. But I did give you a video that I'll show you a bit later. And essentially, the main thing I wanted to do here was to improve the generality. If you're going to use a calculation across many devices in a room, it has to be compatible with all those devices. Now, not everybody's going to have a Tegra chip in their phone. In fact, there's very few mobile devices that actually have Tegra hardware. So the first thing we needed to do, of course, is to convert our implementation into something that is suitable for a whole range of devices, and then examine what we can use to do multi-device communication and determine its scalability. And this is what I decided on as a strategy. The first thing that I did was to actually convert my CUDA code into compute shaders, essentially, and use OpenGL. In fact, OpenGL ES is an embedded version of OpenGL that's supported on mobile devices. And it's not restricted to NVIDIA hardware. It'll basically be supported in some standard will be supported on every mobile device that exists, I would think. And then, of course, in terms of communication, I proposed using Wi-Fi Direct, which is, again, supported by a lot of devices, mobile devices. And this is the highest form of, highest bandwidth form of communication you can actually get on mobile devices, better than Bluetooth and NFC. And this is essentially what it does. Is the application I have has an LBM solver that's built around the OpenGL API, and then we have a peer-to-peer library that essentially leverages, in this case, the Android operating system to perform the device-to-device communication. This is how our grids are structured. So this is an example of two devices. We have the bit that's visible on the screen, which is the blue area, and then we have halo regions that essentially are just there to pass information between devices. So, of course, it's additional compute that we have to do that's not necessarily serving much purpose other than to pass information, but this is a nice sort of simple way of doing things. And, of course, this green region, this halo, is variable in size, which is something that we explore as well, as to see how that has an effect on efficiency. Of course, if you have a small halo, you don't have to pass very much information, but you do have to pass it much more frequently. Okay, the communication strategy that I decided upon was to initially use a kind of master-slave approach. Now, that's probably not the best approach, and I can confirm it's not the best approach, but it is a starter for 10. And the idea is that in a peer-to-peer network of devices, one of them assumes the role of what's called a group owner, and that group owner is used to route these halo buffers around the topology, depending on the number of devices you have. And they're just passed using TCP/IP Java sockets to do the communication between devices. So for testing, I wanted to determine scalability. I wanted, first of all, though, to determine our serial performance, the performance on a single device versus the CUDA implementation, and then extend that to up to 3 multiple devices. So I actually plotted here how long it would take using CUDA, which are the red lines, and how long it actually takes using our GLSL, which is graphics shading language, our shaders, essentially. And you can see that purely for the LBM part, which is the solid lines, they're extremely similar in terms of performance, which means that porting it to compute shaders didn't actually kill performance versus CUDA, which was a good point. Though the overall time, there is a slightly higher overhead using shaders and the OpenGL API versus using CUDA calls, which is something that we can investigate. Okay, so this is our throughput performance, where you can see that if we change what's called the loop per render, which is essentially how many LBM cycles do we do before we redraw the screen, that's actually one of our key variables. And actually what happens is you get to a point where, which is actually clearer by this graph, the OpenGL thread is actually throttled to 60 Hertz, which is actually what the OS tells it can run at. So that's as fast as you can get, even though potentially you could run it faster, which is actually an interesting limitation you don't see with the CUDA implementation. Okay, just to finish off then, when I actually then tested this with variable halo sizes, again, for different resolutions of grid, for 2 devices and then 3 devices, you'll find actually there's not very much difference at the moment. And this is simply down to the communication algorithm that I've implemented. So I'm in the process of upgrading that, changing it and experimenting with different approaches. So I'll show the video. I like to show the video. And at least this proves the fact that you can see, yes, it does work. It does seem to communicate information from one to the other. I should say that out of this, this is periodically linked. So anything that leaves the right-hand side will appear back on the left. But the idea being, this is obviously not operating at what I would determine real time, but it is at a speed where you can interact with it. So it sort of satisfies the requirement of real-time computing, if not real-time CFD. Okay, so just to complete then, our achievements, well, yes, we have proved that we can have multiple devices. We have proved that it's suitable when we implement it in OpenGLES. Although even we have an unoptimized algorithm, we're getting somewhere exciting with it. And finally, these are our recognized challenges, obviously to improve the communication. And that's the things that I'll be working on currently at the moment. So thank you very much.
Okay, thank you. I think in the interest of time, we'll move on. Particularly as we have to try and get the screen back.
I got it.
Thanks.
session then from Dean Day is going to be given to us from Gianluca Paduda, Coventry, who's talking about experimental numerical analysis of a swelling flow and pipe with annular cross-section.
Okay, so welcome everyone. Thanks for the introduction. So the presentation will start with a brief introduction about swirling flows and their experimental and numerical problems. Then I will briefly go through the engineering applications in which they are relevant, and then I will show some of the results of my experimental activities and my numerical modeling, and I will head to the conclusions. So the characterization of swirling flows is quite complex because of the phenomenon involved in the evolution of a swirling flow. From the picture here on the right, we can see the evolution for increasing swirl taken from the study by Escudier. We can see that the flow evolves from an axisymmetric spiral motion to a central recirculation bubble formation going through the vortex breakdown phenomenon. In terms of turbulence modeling, several approaches have been tried in the past, from RANS to LES and DES more recently. However, the problem is that the validation of those models is still missing for the lack of experimental data. For example, we can see that apparently with LES, we can capture some flow structures. However, the authors highlight that it's not yet possible to distinguish between the numerical artificial structures and the real flow structures. In terms of applications, my group is interested in the exhaust after treatment systems. So essentially, my objective is to study swirling flows upstream after treatment systems devices. As you can see, there is a residual swirl component in the exhaust flow due to use of turbochargers in automotive or in general with internal combustion engines. And as you can see, the after-treatment system devices have quite complex geometries, and the key parameters that are required for the design are the pressure drop reduction and the uniformity of the flow upstream. So it's important to correctly simulate the swirling flow. However, swirling flow is present in many other applications, from turbomachinery to aerospace. So we have decided to start with a simplified geometry, so the pipe with annular cross-section. And in particular, we want to characterize the evolution of a confined swirling flow with dipole gradients. These will be relevant for some industrial applications such as heat exchangers. So this is a picture of my test section. Air is flowing through a swirl generator and then goes to the actual test section and discharges in open ambient conditions. Just a quick look at the swirl generator. It consists of moving blocks and fixed blocks. By moving the position of the moving blocks, we can generate swirl up to 1.51. So what I have measured are the static pressure distribution at the external wall of the pipe and the velocity at the outlet section. Further experimental data are coming from a parallel PhD project on more complex geometries. So we can have a look at the pressure measurements results. In particular, it's interesting to highlight that the three mass flow rates considered exhibit a similar trend for increasing swirl levels. So this is first result. The swirl number is dominant within respect to the Reynolds number. The other thing that we can get from these results is that there is a radial pressure gradient, so the flow is pushed towards the external wall. Similar considerations can be made from the velocity distribution at the outlet. So we can see that there is a similar trend for the three mass flow rates considered. And as we move with, as we increase the swirl number, the flow is going towards the external wall of the pipe. before showing the first results of the numerical model, I want to highlight the effects of the inlet and outlet boundary conditions. Even for a pure axial case, what I have tested is that if I consider just the simple test section, I get a pressure distribution that is the red line here. But if I include an extended domain, so a sort of chamber at the outlet section, I can achieve a better agreement with the experiment. And if I include this swirl generator geometry, I can achieve a better agreement at the inlet. However, both configurations increase the computational time. So for this first numerical model, I'm just using the swirl generator because I'm more interested in the swirl levels. So we can see here an animation of the streamlines with the increasing swirl levels that I have considered. I'm using a commercial software, and I'm solving steady-state simulations with the K-epsilon V2F model. What we can notice is that with the increasing swirl, there is an increased tangential component of the velocity, so the flow is pushed radially towards the external wall, and there is an extended flow path. However, if we compare with the experiments, the agreement is still poor. What we can see is that the general trend is captured. So for the increasing swirl levels, we can see a similar trend in the pressure distribution. But in general, the pressure is over-predicted by the model. In terms of velocity, what is interesting to notice is that while for the low swirl levels, the velocity is quite well predicted, with the increasing swirl levels, the inner part of the annular pipe is less in agreement with the experiment. So I've tried to compare several eddy viscosity models from the standard K epsilon to the K omega SST. However, they don't seem to improve the agreement with the experiments. So it's a problem related to the eddy viscosity formulation itself. So essentially, all the models that I have tested fail to predict the A-radial pressure gradients and the high radial redistribution of the velocity. And in particular, they fail to predict the anisotropic turbulence levels. One of the key parameters that is commonly used, as I said, is the swirl number S. So here we can see that with increasing swirl levels, there is a swirl decay in the pipe. And in particular, with the maximum swirl level that I have considered, the swirl decay is more rapid. And this is in good agreement with the observation made by Clayton and Morsi in one of the experimental papers of the past. However, what we can see is a rapid decay for the high swirl cases near the outlet, confirming that it's necessary to extend the domain to fully develop the flow. In terms of the models, once again, the other viscosity models, they don't seem to perform better than the V2F model. And it's interesting to notice that they all fail to correctly match the experimental value at the inlet calculated in a previous activity. So in conclusion, what I have done so far is a preliminary experimental and numerical study of swirling flows in an annular pipe. There are several challenges in the modeling that we are trying to address. We have refined our experimental methodology to capture the high radial gradients of confined swirling flows. And we have a first set of experimental data for the CFD validation. The inlet and outlet boundary conditions are crucial to correctly model the swirling flows, and we are now investigating new approaches to reduce the computational time. In general, Ron's eddy viscosity models fail to correctly predict the behavior of swirling flows. However, some qualitative results can be captured even by Ron's eddy viscosity models, and this is important for industrial applications. As a future work, we will test more complex geometry, and we will run some LES models to further explore swirling flows, and we will use PAV to collect more data for the CFD validation. So thank you for your attention.
Thank you. Time for a question or two. Okay, well, you have one. Oh, go on then.
So, I mean, to get that inlet velocity correct, I mean, what you didn't show us very much was like, I don't know, the mesh refinement or the grids you're using to actually capture the geometry, for example, in that part of the flow. I mean,
yeah.
Presumably you've tried experiment with varying how well you resolve that geometry at least, and whether that affects.
Well, I've performed a mesh-independent study on that from the simulation point of view. So this is mesh-independent, so it's not grid-dependent. In terms of the experimental inlet condition, the swirl generator is based on previous published studies, and essentially it shouldn't affect the evolution of the swirl, if that was the question.
Okay, well, I was just wondering if we quite captured accurately enough the geometry of the inlet, it's not getting the correct velocity distribution. But you think it's to do with the turbulence model rather than the...
Yeah, it's the turbulence model, because...
So this starts into, is it the wall functions and things like that?
Well, with the V2F model, we are using the wall functions because they are embedded in the model. However, it's not just a problem of the wall function itself. It's, especially with the increasing swirl levels, the flow is highly anisotropic. So the main reason, we think that the main reason of the fail of the agreement is the anisotropic level that is not computed by the eddy viscosity models that we have considered. So we are trying to expand it with the Reynolds stress model that should give better results, but we think that the only option is LES for the iSwirl cases.
We can have a quick chat afterwards. I think nonlinear models and RSM have been shown to be quite effective for this.
Yeah.
But I think we'll close the session and thank all the speakers and enjoy dinner.